We are going to be finishing up with randomization algorithms from last lecture, from the classes lecture, and then we're getting into hash tables, which will be the first data structure we'll consider this semester. Before we do that, just wanted to again announce that we have a midterm. That midterm, That midterm will be, the coding portion will be in lab on Wednesday, February 14th, and you'll be allowed a one-page cheat sheet front and back. And then an in-class exam Thursday, February 15th, and no notes. No notes, no cheat sheet, no electronic devices. Whoops. Yeah. No cheat sheets, no devices. Okay? And the things I would put on the cheat sheet, it's worthless to put definitions on the cheat sheet. What you need are code fragments that show you examples of how to write things like string streams, or with string streams, how to extract integers or strings from string streams, how to check to see whether what you read is valid, how to recover if it's not valid by clearing the jam and then reading it into a string. Examples of how to iterate through 2D vectors. Examples of how to resize 2D vectors so that they have the right shape. Both when you know in advance how many items will be in that 2D vector and when you do not know in advance what will be in that 2D vector. So you need code fragments that you can adapt to the problems that you're given. There's going to be two coding problems. And as I said the other time, it will be up through 2D vectors. You have not yet had an opportunity to program with classes or with hash tables. So the coding portion is up to 2D vectors. Now, the in-class includes everything through Tuesday. So it will include hash tables. Okay, so I expect you to be able to read things or fill in hash tables, do bit operations, which we'll be talking about over the next 2 days. So questions about that? Yes?
So is the in-class one primarily multiple choice?
No. There's no multiple choice on it. It is all, there's one fill in the blank with some terms, so you need to be familiar with terms, but it's things like, here's a hash table, fill in the hash table. You go to the exam section, that's a good example of what you can expect. If you look at that, there's no multiple choice on it. The closest you come is some fill in the blank like that. Yes?
Are there any limitations on the cheat sheet? Like, is it all to be on the front?
No, I said front and back. One page front and back. If you can put it in 8-point font and read it, that's fine. Okay, they will be collected, so you need to put your name on them and they will be collected.
Do you want it to be like a paper type? Like, is your paper
8.5 by 11.
Okay.
Okay. Yes, yeah, I know. Yeah, you can't bring in a poster board. It needs to be 8.5 by 11. Other questions? Okay. Then on one thing on the labs, when you're doing the labs, I've noticed, again, I know I have to keep saying it, but it bears repetition. One is incremental programming. Okay, that's just vitally important. Incremental programming. So just build them incrementally. The second is use pictures, work through concrete examples first. And figure out how you would do it by hand. Because if you don't do that, it's really going to be tough to program it. You really need, when you figure out how you would do it by hand, that is generally gives you the basis for your algorithms. Okay? So for example, on this particular lab 3, one of the problems is to rotate a PGM file counterclockwise. Well, it really helps if you first figure out what it looks like when it is, actually clockwise in this case, what it's going to look like when it is clockwise, and where the different rows will go. So for example, figuring out that the top row is going to end up as the last column, and that the second row ends up as the second to last column, and then figuring out how does each row map to something there. So you can start to see that row 0 maps in this case to column 2, row 1 maps to column 1, and you would see that row 2 maps to column 2. And from that, you have to start abstracting. What does that mean about row I? What column does row I? Whoops, this is column 0. So you need to start abstracting. Clearly, some row maps to a column. So if you're given an arbitrary I, what column does that map to? And presumably, it's going to be some function of this I. Now, I'm not going to tell you because that's something for you to figure out, but that's what we want with problem solving. Problem solving is learning how to solve these problems. We're not going to tell you how to do it in this course. You have to figure it out. We're going to give you hints like this, work through a concrete example, and start writing down how things, in this case, rows map to columns, and then you should be able to start writing your loops. The third thing is, I heard, and if I'm wrong, I apologize, but I heard that one of the TAs may have told you that once you have clockwise working for lab 3, that you could simply implement counterclockwise, that you should simply call clockwise 3 times. Okay, which works, okay? That does work. Okay, it's a very good insight. However, I don't want you to do it that way. Why do you think I don't want you to call clockwise 3 times, even though that works? What? It's inefficient. Okay, it takes 3 times too long. And efficiency is an important issue. So I don't want you to do it that way, even though it's a clever observation. And it would certainly simplify your code. But it takes 3 times too long. Okay, in fact, you should simply copy and paste. Whichever one you do first, you can copy and paste that code because only one line changes. The line that copies pixels from the old image into the rotated image. All the other lines are identical between the two routines. So in fact, you can still do it very simply. You just have to figure out what the right equation is for doing the transfer. Okay, so we all clear on that? Very good. So then I want to move on, and what I wanted to talk about first was randomization, because it's a very big issue that comes up again and again. Okay, that's what Powerball does. They have to randomize. I know they use ping pong balls, but often people come in, they want a set of random numbers for Powerball. A computer generates the random numbers. Or in games, to prevent the players that you don't control, the computer-controlled players, from not always behaving predictably, you need to randomize their behavior. So what is important is being able to generate random numbers and then being able to randomly shuffle things. Okay, well, C++ and C give you random number generators. Dr. Planck likes the rand48 functions. So you see him using, I believe, lrand48, drand48. These are functions that produce random integers and random doubles. Okay, and they are between, essentially they are span the full range of integers and the full range of doubles. Okay, and then there also is a seed, if you remember, and I forgot to look that up. I believe it's just I forget if it's srand. I'm going to say srand48, but I'm not 100% sure. You give it a seed, and you only call srand48 once. So that initializes the random number generator. And after that, you simply call the lrand48 or drand48 with no parameters. Now, you have to use these random numbers in some way. Remember, they're generally from -infinity to +infinity, so you're having to use them, and of course the way you use them depends on the application. So Dr. Planck's application was to randomize how pictures appear in his table. So he doesn't want the pictures to always appear in the same order. He wants them to appear in different orders. And you can see here he has 18 pictures, and he has them stored in a vector that has 17 elements. So what he wants to do is a pretty common thing. He wants to randomize these pictures. Okay, so he wants to randomly shuffle them. And he goes through 3 algorithms in his notes. The first one just says for essentially I equals 0 to 17. Now I'm using pseudocode. Generate, so this is strategy 1. For I equals 0 to 17, generate a random number between 0 and 17 and output that picture. Okay, now I just realized I did make one incorrect statement back here. I said that they went from -infinity to infinity. It's actually 0 to infinity. They give you positive numbers, so I apologize for that. They give you positive numbers, non-negative numbers. Okay. So how do you generate, if you've been given a number between 0 and infinity, and you want to generate a number, so you have that number now, let's say in num, how would you convert that number to a number between 0 and 17? Modulo. Modulo what? Modulo 17 or modulo 18? We'll take a vote. How many think it's modulo 17? How many think it's modulo 18? You're right. Very good. because it's the remainder. If you remember, modulo is the remainder. So the remainder can be any number between 0 and 1 minus what it's divided by. So to get a number between 0 and 17, you mod by 18. Now, this turns out to be a bad strategy because Dr. Planck wants each image to be represented exactly once in his output. Does this strategy guarantee that each image will be output exactly once? No. Why not?
It's randomized.
Right, which means what?
There's a chance to pick out the same number between 0 and 7.
Very good. Since it's random, there's a good chance he'll pick the same number between 0 and 17 twice. In which case, he will, by definition, not pick some other number between 0 and 17 ever. So this is not a very good way of going about things. I think, see, I ran a test way at the very bottom. Not there. In the hashing notes, I ran it. So, if you just run a random number generator, there we go. On average, it's going to generate about 78%. So 78% unique numbers, 79%, which is not enough. So in general, if you generate a bunch of random numbers, only about 78 to 79% of them are going to be unique. Okay, so the problem is only about does not guarantee all images are output. In fact, it's only about, on average, 78%. Okay, so that's not particularly good. So it's simple, fast, but not particularly good. So strategy 2 is one I'll simply, let's see, I think he has a good set of notes there, so let's actually just look at what he had to say. Okay, well, we have to. So what he's going to do is he is going to create a array, again, up to the number of images. And what he's essentially going to do is start by saying that they are, is he going to say true or false? So he is going to say, initially, false. So every one of them has not yet been output. Then he's going to generate a random number. So he's going to say basically for I equals 0 to 17, he's going to generate a random number. Okay, and so he's going to do a do while, and again I'm using pseudocode. So in fact I'll just say do, generate a random number. From 0 to 17, while we'll call this here, he called it random, so we'll call it in random. So he's going to keep generating random numbers until he finds one that is false. So basically, if it's false, that image has not yet been output. So this is kind of like the previous algorithm, except that if he generates a random number that's already been used, he throws it away and generates another random number. So it's just an improvement on strategy 1. Okay? So the first time through, he's guaranteed success. Let's say that it's 2, so he changes 2 to be true. Now let's say the next time through, he generates 2 again. Well, he would find that 2 had already been output, so the while is false. He would come back up and generate another random number. Maybe this time it's 17, so he sets 17 to true. Okay, and he keeps doing that 18 different times until he has completed his outputting his images. Okay, so when he's done, so when he comes out of his do loop, he outputs image num and sets in random of num to true. Now, this works really well early on. Early on, almost all the entries are false, and you have a very good chance that the number you select will be a new number. And even if you select a number that was previously selected, there's a good chance that the second number you select will be unique. But the situation changes once you have output most of your images. Once this array right here is nearly full, now the chances are you will be generating random numbers that match previous random numbers. And you'll have to do that for a fairly long time. Okay? Now, you haven't really been introduced to the expected values for that, but it turns out that roughly speaking, the expected number of random numbers that you have to generate per iteration is that figure. So when I is 1, when I equals 1, there's an excellent chance that you don't have to. So this is the expected random numbers to get a unique one. Okay, so very early on with I small is close to 1. So when I is very small, so when I is close to 1, then this thing is roughly 1. But when I becomes I divided by, or n divided by 2, what is it? What is this thing when I becomes n divided by 2? That is, it's half full. So that's n minus I. So it's n divided by n minus n over 2. What's the bottom resolved to? N over 2. So what's the value? 2. So when it becomes half full, on average, we expect to have to generate 2 random numbers to get a valid one. What about when I is approaching n? How many do we need? As I approaches n, what's that curve look like? Come on, you've had this in calculus. Positive infinity is what it approaches. Okay, that's not very good. In fact, it's pretty bad. Okay, so in fact, you can do a summation, and again, you haven't seen this yet. When you get to ECE 313 or another stat course you may take in your major, you will see how to sum up these sequences, and you'll find that it is roughly n natural log n, which isn't particularly grand. Okay, it's not particularly bad either, because the natural log will take things down pretty quickly. But nonetheless, it's not great. Okay, and there is a better way. Okay, and that better way is to essentially generate, so strategy 3, let's now go to strategy 3, is, again, we have this array. But now what we're going to do is we're going to work from the back, kind of like you did with pad. And the first thing we're going to do is what we're going to do is shuffle stuff, like shuffling cards. So the first thing we're going to do is we're going to shuffle 17. We're going to select a number between 0 and 17, and whichever number we come up with, we're going to swap 17 with it. So let's say that that number was 2. So now we will shuffle 17 and 2. And that turns out to be the permanent repository for 2. Now we move our pointer back 1 to 16, and we're going to shuffle 16 by generating a number between 0 and 16. Let's say the number is 2 again, which before would be bad, but now we simply exchange 16 and 17. Okay, now we go to 15. We generate a random number between 0 and 15, and we again swap the 2. Okay, when we're done, it turns out we have a well-shuffled array. Okay, he has a further example in his notes. So here he's shuffling an array that has 5 elements. So initially it's again 0, 1, 2, 3, 4. When he does, the first number to be generated is 2. So he's going to shuffle 2 and 4. And you can see over here 4 and 2 were shuffled. Now he's going to generate a number between 0 and 3 because that's the next one, and he generates 1. So he's going to swap 1 and 3. And you can see over here 3 and 1 got swapped. Now he generates a random number between 0 and 2. The random number is 2, so in effect no swap happens, which is fine. It simply stays, the number stays there. Then he generates a number between 0 and 1, and he swaps 3 and 0. Now, is this last one necessary? Does he have to do this last step, where he generates a random number between 0 and 0? No, why not?
Because
There's only one option left. It's going to stay there no matter what. The only option is 0. So, in fact, he could simply go from I equals 4 down to 1. So again, we just worry about these little efficiency things. So at any rate, when you're done, you're guaranteed to have a randomly shuffled array. Okay? And you can see the code. He actually goes all the way down to 0, but really he could have gone down to 1. And he's just generating his random number, and then he's just doing a swap. Okay? So, how many random numbers do you have to generate for this one? If I is equal to n, how many random numbers do you need to generate? What's the maximum number? About n, yes. Okay? The reason is you're only generating one random number per loop. You execute the loop n times because I is equal to n, and you're generating 1 per loop. So you generate at most n random numbers. That's better than n natural log n. It's what we call a linear algorithm. And it achieves our goal of a shuffled array. So the third strategy is the best strategy. Because the first strategy was the worst. It was fast, but it did not output every image. The second one at least output every image randomly, but it was slow. So third one is like Goldilocks. It's both efficient and it randomly shuffles. Okay, so questions about that? Okay. So, in that case, we have officially finished the review of CS102 material. And we are ready to move on to the meat of the course. Actually, we've seen some of the meat of the course because you were being introduced to new C++ concepts. But we have something new to consider, which is data structures. And what we are going to care about for the rest of the semester is data structures that can efficiently implement the following operations. Find. This is a common operation. Find a data element, insert a new element, and delete an element. So we are going to be concerned with the rest of the semester with finding data structures that allow us to organize data so that we can efficiently implement these three operations. This is what Google is concerned with. When you do a Google search, it wants to efficiently find links that are related to your search. It needs to keep adding links to its database. And when links become stale or when it discovers one that is malware or bad, it needs to delete that link. Okay? So data structures organize data so it can be searched efficiently. Data structures organize data so that, actually I'll say so that the data can be processed efficiently. And processed efficiently depends on the operations that we care about. Okay? We don't always care about find, insert, and delete, but that's what we care about in this course. And as you might imagine from insert and delete, the data sets are dynamically sized. So an important thing is that the data sets have dynamically changed. Okay, you may remember in CS102 you were taught an efficient technique for searching arrays. It was called binary search. Okay, if you may remember, binary search says we're going to look at the element in the middle. So let's say we're searching for 20 and the middle element is 40. If we look at the middle element and it's 40, where do we know that 20 resides? In the left part. So we know it resides in this part. So we eliminate half the array. And again, our next search will be in the middle. Maybe it's 10. Now where do we know 20 is? In the right side, right here. So at each point, we look in the middle of the remaining part of the array, and we eliminate the half where the search element can't be. And it turns out that in log 2 n searches, it can determine where the element is. It takes log n to n searches to find the element. And that's much better than a linear search when n is large. If n is equal to 1,000,000, meaning there's 1,000,000 elements in the array, then a linear search would have to potentially examine all 1,000,000 elements to find the value. Whereas log 2 of 1,000,000 is something like 20, much smaller. Now, binary search rests on two assumptions. What's one assumption that the most important assumption about binary search? Yes? Your data is already sorted. Very good. And the second assumption is that the data is static. That is, it doesn't vary. You don't do inserts and deletes. The reason that is the case is because inserting or deleting an element from an array is very expensive. If I have 1,000,000 elements in that array and I delete something near the front or I insert something near the front, what I have to do is move all the elements to the right by 1. Okay, which is almost 1,000,000 elements. So it's very inefficient to insert or delete elements from an array, unless it's the last element. It's fine to insert or delete the last element using pushback, or there's a comparable one for popping one off the back of an array or vector. But otherwise, it's really expensive, and we'll look at that later in the course. But you don't want to be inserting or deleting from the middle of a vector. So binary search doesn't work very well on dynamic data sets, which is what we're considering. So we want to figure out how to do it efficiently on data sets that can change dynamically. And the first thing we're going to consider are hash tables. Okay, so hash tables are the first thing that we're going to consider. We'll also consider trees later and linked lists. But hash tables are our first one, and they're actually going to be implemented, believe it or not, in a vector, which you might find interesting because I just said, well, vectors aren't necessarily a particularly good way of doing it. But I am not going to be using I'm not going to sort them. Hashing is going to relax the assumption that the items need to be sorted. Okay? What they're going to do is they are going to randomize. Remember, we just said that's important. They are going to randomize keys. Okay? So they're going to take a key, and it's called the hash function. So H stands for the hash function. And it's going to map it to a value between 0 and the table size. We call the size of the vector the table size. So we'll map it to a number between 0 and table size minus 1. Okay? So for example, let's say we have these 4 keys: Luther, Rosalita, Binky, and D'Antonio. Let's just say we have a hash function. That's one of the things we'll be discussing, so don't worry about how we generate these hash values, but let's say we have a hash function that generates these values. Clearly, they're too big for any hash table we're going to have. We're going to use a hash table of size 10. So how do you think we can map those enormous numbers to a hash table of size 10? Modulo. That modulo operator keeps popping up, doesn't it? Okay, you better become friends with modulo because it is a very valuable operation for programmers. So what we're going to do is we're going to mod the hash value by the table size. So our table size is 10, so you can pretty much see that the remainder is going to be the last digit. Hopefully you can see that that is the case. So Luther is going to have a value of 1, Rosalita will be mapped to entry 4, Binky to entry 2, and D'Antonio to entry 1. So Luther is our first one, and we put it in entry 1. Then we put Rosalita in entry 4 and Binky in 2, which was all well and good because those entries were unoccupied. But what happens when we get to D'Antonio? It's already occupied. D'Antonio wants to go where Luther is already located. We call such a situation a collision because the entry is already occupied. Okay, we should expect that. Remember, I said that if you generate 100 random numbers, roughly only 78 to 79 of them are going to be unique. On average, the other 21 or so are going to be duplicates. So no matter how good our hash function is, if it's generating things randomly, there are going to be these collisions. Okay? So it turns out a hash table has these 3 characteristics. There's a hash table, which is a vector of some size. There is a hash function, which is meant to randomize the key. And there is a collision resolution strategy that is meant to decide how to handle the case when 2 keys want to go into the same entry. Now, the book uses a term that is commonly used, a bucket. So you will also hear me refer to the various entries in a hash table as buckets, because literally sometimes we're going to dump multiple entries into the same bucket, and buckets hold things. So a common term that you hear with hash tables is buckets. All a bucket is one entry. A bucket equals one entry in the hash table. Okay? So, the operations for the initial operation for insert and find is pretty easy. Okay, you simply, actually in for delete, all of them, the initial one is essentially you take a hash function, apply it to the key, and then you mod it with the table size. And that will give you something between 0 and table size -1. So that's the bucket you're going to look at. So initially, you look at that bucket. And the easy case is with insert is that the entry is empty, in which case we simply put it there. If it's not, we have to employ a collision resolution strategy. Now, the simplest strategy is something called separate chaining, something you read about in today's readings. Separate chaining says we're just going to put everything that maps to the same bucket in that bucket. Well, how do we do that? We can't, obviously, if we simply store D'Antonio there, we overwrite Luther. So obviously, it's not as simple as simply saying, well, we'll put the entry there because it could overwrite whatever was previously there. But we have a solution. It's called 2D vectors. Okay, what is going to happen is each of these entries is actually going to be a 2D vector. So in fact, when we get to D'Antonio, we're simply going to push D'Antonio onto the vector for bucket number 1. Now, unlike the PGM ones, the vectors will have different sizes depending on how many elements are in each bucket. So some buckets will have 0 length vectors because they'll be unoccupied. Right now, 0, 3, 5, 6, 7, 8, 9 have 0 size vectors. Right now, Binky and Rosalita have vectors of size 1. And once we add Antonio to bucket 1, then it has a vector of size 2. So each bucket may have a different sized vector. That's fine. It will have a vector equal to the number of entries in that bucket. So that separate chaining is actually very simple. So essentially it comes down to these three, and we're going to use pseudocode, which you should get used to using. So with separate chaining, the insert is essentially take a key and a hash table, which we'll call table. So essentially we just get the bucket. The bucket is equal to our hash function applied to the key, mod the table size. And how do we know what the table size is if it's a vector? Dot size. Okay, and then we simply do a table bucket dot pushback, and that will push that key onto the appropriate buckets vector. Very simple. Okay? So find is pretty simple too. Find is like delete or insert in that you find the appropriate entry. So find, you're going to find the appropriate bucket, and then what do you think you're going to do once you found the appropriate bucket? Search linearly through it. Now linear search is fine here because we expect the buckets to be pretty small. We'll get to that in a moment. So find a key and a table. We're again going to get our bucket. And now I'm going to really resort to pseudocode and just say table size. And now for I equals 0 to bucket size. And again, you should be able to figure out how to get this. Whoops. Well, here we'll make it a little easier. Do it. So to get the bucket size, that's really going to be table bucket. So that gives us the vector for that bucket dot size. -1 because we don't want to step past the end. And we just are going to do a linear search. If table bucket, so that's the, gets us entry to the bucket I, is equal to the key, we return key. And if we get outside of it, we return false to indicate that we were unable to find the key. So find is pretty simple. And delete is very much like find. Because what is the first thing delete has to do? It has to find it. So if it finds it, this line return key changes. Okay, we delete the key from the bucket. Now, I told you that it was fairly inefficient to delete something from the middle of a vector. And yet that's exactly what I'm proposing to do. Let's say the key is right there. And if I delete it, I'm going to have to shove all these entries to the left. Can anyone think of an easier, more efficient thing I could do, given that I know that the entries are unordered, that order doesn't matter? Very good. I could simply swap X with the last value in the bucket because order is immaterial for a hash table. So actually what I can do is swap Y and X. And now it's super efficient to delete something from the end of a vector. So that's a cute trick. What delete is going to do is swap bucket, well, table. Let me get this. It's going to swap table, bucket, I, and table, bucket, last element. Okay, so that's going to be the size minus 1. I'm just going to say last element. In fact, you should be able to do that, so swap that and last element in the vector. Then delete last element. That's very easy and very efficient. And then we return. Okay, so that's delete. So separate chaining is a very appealing, very simple algorithm. Okay? Very easy to code up, yes.
What happens that like the table has only contains one item?
No worries. Then if you swap an element with itself and delete it, it becomes a vector of 0 elements. It's not an issue. I guess you might want to check to see if there's only one element so you don't have to do the swap. Okay. Yes?
And is your bucket index just going through the individual values in a singular bucket?
When you say bucket index, I think of this as my bucket index, and that never changes. Once you've computed it, are you referring to this index or this index?
Just for a table bucket, just like table bucket of I, just wanting to know what direction is what.
So this is always looking at the same bucket, and then this is going through the entries in this bucket.
Okay.
Okay?
Okay.
So this is always, table bucket is always the same bucket. And this is just the vector associated with that bucket. Okay? You good with that? Okay. Well, if you think you're good with that, I know you did an example, but we're going to do another one. Let's see if you could do it for a midterm. So, let's look at the midterm from last time. Don't worry about the linear probing, but see if you can do this one from, if you have it, you can also do it. There's 13 entries, it doesn't go from 0 to 9, it goes from 0 to 13. And it's 32, I'm going to write them down. You're going to be doing 32, 49, 19, 52, 58, and 15. So you want to put these 6 values. Don't worry about quadratic probing. We haven't covered it yet. I'm only going to give you about 2 minutes for this. Okay. So let me go over them. So you start with 32. 32 divided by 13 is 2 with a remainder of 6. You divide 13 into 32, you get a remainder of 6, and that's what the mod operator returns. Mod returns, remember this returns the remainder. Okay, so 32 mod 13 is equal to 6. So we put 32 into bucket 6. Then 49 mod 13 is 10. The remainder is 10, so 49 goes there. 19 mod 13 is 6. That's a collision, but we don't care. We simply add 19 to the bucket for 6. 52 mod 13 has no remainder, so it goes into location 0. 58 mod 13 is yet one more collision at 6, so it goes into that bucket. And 15 mod 13 is 2. So it goes into bucket 2. Now I made it a little harder on the exam. There's a couple more keys on the exam, but I guarantee you you're doing separate chaining on the exam again. Okay, so this would give you the answer for separate chaining. There are questions about that. Okay, so that's one collision resolution strategy. Okay, and it's pretty simple. In fact, it's the one that's most commonly used when you have plenty of memory. But there is another approach that you can use when memory is more at a premium, and that is called open addressing. So open addressing, separate chaining used a 2D vector. If multiple entries hashed to the same bucket, we simply put all entries in the same bucket. With open addressing, we're only going to use a one-dimensional vector, which means that if two items hash to the same bucket, we can't put them both there. One of them has to go someplace else. And the reason we say collision resolution strategies 2 through 4 is that we're going to discuss 3 different ways to handle that. Now you will read about this actually in the reading for next time, but I think I can go over it at least starting today because it's pretty simple. So all of them are actually, rather than worrying about his function here, we'll get to that later. Don't worry about that for the time being. Instead, we'll discuss it intuitively. The first one is the easiest. It's called linear probing. And what it does is it says, if there is a collision, then we will do a linear search until we find the first empty bucket, and we will put it there. So the collision resolution strategy for linear probing equals do a linear search for the first empty bucket and insert the element there. And if need be, wrap around. Okay? Wrap around if necessary. Wrap around if you reach the end of the table. Okay, so that's pretty simple, I think. So when D'Antonio hashes to bucket 1, using this strategy, where is D'Antonio going to end up? In bucket 3, because that's the first empty bucket. Could someone see what might be a potential improvement on this strategy? What would happen? It may become more clear. What if I now insert Brad and Brad also collides at 1? It wants to go into bucket 1. You'd have to search all the way to 5, which is kind of inefficient. It'd be quicker if you could search backwards. We won't do that, but some algorithms will look right, then look left, then look right, then look left. But we're not going to do that. We're just going to look right. Okay? Yes.
It'd be tough to find what you were looking for if it wasn't in the bucket that you expected it to be.
So we'll get to that. Okay? So that was insert. Okay? Now let's do find. So let's try to find D'Antonio. Okay? D'Antonio hashes to bucket 1. It's not there. Now we start searching right until we either find D'Antonio, which we do in this case, or let's say we were searching for Brad, and let's say Brad hashed to 1. If we find an empty bucket, then we know that Brad was not in the hash table. So basically, to do a find, we simply go to the bucket where we expect to find the key. If it's not there, we start searching to the right until we either find it or we find an empty bucket. So this was insert. Find is simply go to the bucket where the key hashes to. Okay? Do a linear search from that bucket until A, you find the key, or B, you find an empty bucket. Okay, if you find an empty bucket, it means that the key is not in the table. So it's actually pretty simple. And The third thing is delete. That seems pretty simple too at first glance. It seems like you first find it, and then you mark the bucket empty. Let's try it. Okay? So I'm actually going to add Brad and assume that Brad also hashes. I'm going to assume that h of Brad is equal to 1. So I'm going to put Brad in 5 because after D'Antonio goes into 3, 5 becomes the first empty bucket. Okay, now I'm going to delete D'Antonio, which seems simple. I simply find it, and then I mark its bucket as empty. Exactly. Now if I try to find Brad, I first run into an empty bucket and I inaccurately report that Brad was not in the hash table. So there is a solution. We don't mark it empty. We mark it as empty but previously occupied. Okay, so there's ways to do that. In fact, you're going to have to do it in the lab. So what delete does is it marks something as empty but previously occupied, and then you modify this until you truly find an empty bucket. So if you find an empty but previously occupied bucket, you keep going. Okay? What do you think, though, kind of happens if this hash table is in existence for a long time? What happens probably to all the buckets? They're either full or they're labeled empty but previously occupied, which means that over time, if you're not careful, how long is it probably going to take to do an unsuccessful search? Or even a successful search if the item is fairly deep in the array. Order n. It's going to probably, you're going to end up searching the entire vector. So this approach doesn't necessarily work as well when you're getting a lot of deletions. It's not bad if you're having just inserts and finds, but if you start to mix in a bunch of deletions, over time, you start getting a lot of empty but previously occupied. So this strategy typically isn't as efficient as separate chaining is. Now, a big thing that we haven't discussed, and it's the last thing we'll discuss today, we'll get into some other collision resolution strategies on next Tuesday, but you could increase the table size. So a big component of making hash tables work is choosing your table size. If you can make that table size big enough, then maybe even if you do some deletions, it won't be as big of an issue, because if we have a huge table and not so many entries in the table, we might be okay. And in fact, there is a very important term, we'll end with this very important term, it's called the load factor. The load factor is intuitively the percentage full equals percent full. So it's the number of data elements divided by the size of the table. So in our table, there were 4 keys and the size was 10, so the load was 0.4. So in general, there are some general rules for the table size. For separate chaining, we try to make the load equal 1, which means separate chaining prefers a load of 1. Which implies that the number of data keys equals the table size, roughly. Because you don't know in advance how many keys you're going to have, so you have to take a guess. For linear probing, we have to create extra space. With separate chaining, it's okay for there to be collisions. With linear probing, we're not as happy. So for linear probing, we try to keep the load less than 0.5. Okay, it just turns out, we'll get to an analysis of that, but it turns out that a load of less than 0.5 generally means no more than 2 probes to find things. So that implies that the table size is equal to what? Times the keys. If the load needs to be less than 0.5, the table size should be greater than what?
Twice.
2 times the number of keys. So we have to estimate the number of keys and make our table size at least that large. For separate chaining, we can make the load about 1 because it turns out that means that on average, how many keys per bucket if the load is 1 in separate chaining? If they're randomly distributed, how many keys will you expect there to be in a single bucket? 1. Okay? If their load factor is 10, you'd expect roughly 10 keys per bucket. Okay? And we'd like to keep it around 1 key per bucket. So that's why a load factor of 1 is good for separate chaining. Turns out with linear probing, having the table about half again as large as the number of keys gives us enough of a cushion in terms of empty buckets to make it efficient. Please read the bit notes for next time. It's not just the book. If you come to class next time and you have not looked at the bit notes, which are buried here somewhere in the middle of Dr. Planck's notes. These are notes I wrote because students were so confused by bit functions, even though you should have seen them in 130. If you don't read these notes and you come to class next time, it will be one of the most blow-away classes of the entire semester. Okay, even with reading it, it will be one of the hardest classes of the entire semester on Tuesday. So read those notes.